Hello everyone, myself Piyush Fogart from Netaji Subhash University of Technology, Department of Physics, Dwarka, New Delhi, and I will be presenting on coexisting dual morphology of single-phase molybdenum trioxide, unlocking the enhanced electron transfer characteristics. So the content of the presentation will be the introduction part, result and discussion. We will discuss about XRD, crystallite size and strain, the UV spectroscopy response and morphological analysis and electrochemical analysis, and then conclusion. So for the introduction, why are we talking about MO3? So MO3 is a well-known transition metal oxide. It has a unique electronic and optical properties which can be used in solar energy conversion. But the morphology of any material plays an important role towards its functionality. So that's why we are talking about dual morphology, the advantages of dual morphologies. So the coexistence of dual morphology can effectively enhance the charge transfer and functionality in a solar cell, and the long surface to volume ratio in a nanorod can offer improved material capacity to enable effective charge transfer, whereas on the other hand, the spherical shape of the material can boost electron transport and add to the material's overall stability. So what is the application of MO3? It can be used in catalysis, flame retardant, ceramic material, photocatalysis, medical application, and corrosion inhibitor. So moving on to the synthesis part of the presentation. First, we have taken to synthesize dual morphology of MO3, we have taken 0.23 molar solution of ammonium morydate and stirred it for some time. After that, we had adjusted the pH to 1 and then transferred the solution to an stainless steel autoclave. And then the autoclave was placed in a hot air oven at a temperature of 180 degrees Celsius for 12 hours. After the cooling of the autoclave, it was centrifuged and washed with 3 times with distilled water and 3 times with absolute ethanol, and then it was dried, and this is the fine powder of MO3. So for the XRD diffraction pattern, we can see that the single phase molybdenum trioxide is present with a JCPDS fine as shown on the right side of the figure with an orthorhombic structure. The 3D module of orthorhombic structure is shown here. You can see the presence of oxygen is higher than the presence of molybdenum atoms in an orthorhombic structure. So talking about the crystallite size and strain being an important part of a nanomaterial, we have calculated the crystallite size using Debye-Scherrer equation for the single phase molybdenum trioxide, which came out to be 29 nanometer. Now, Debye-Scherrer equation works on the assumption that there is no strain present in the material. To know if that there is strain present in the material, we will use the lattice parameter. We have calculated the lattice parameters for an orthorhombic system using the equation, and we find out that there is a deviation between the as synthesized sample and the JCPDS fine data, which means that there is some strain present in the material. So to calculate the strain of the material, we have used another equation known as Williamson-Horne equation, and the graph shown on the right. So using the value of slope and intercept shown in the figure, we have calculated the crystallite size to be 34 nanometer. However, there is randomness in the behavior of the peaks due to the full width half maxima. So to stabilize that, we will use size strain equation, in which you can see we have used Ritwind analyzed data, which will provide an average full width half maxima and give us size of 26 nanometer, which is more accurate than Debye-Scherrer and Williamson-Horne equation. Moving on to the optical absorption of the material, we have performed diffusion reflectance spectroscopy for the as synthesized molybdenum trioxide, and the absorption plot shows absorption only in UV region from 206 nanometer to 289 nanometer. The band gap was calculated using a TOC plot, which came out to 3 electron volt. The morphological analysis of this material is a very important part. As you can see that there is an existence of dual morphology. On the upper part of the micrograph, you can see nanorods, whereas on the lower part, you can see the nanospheres. At a higher magnification, you can see the presence of nanorods and nanospheres, which is the novelty of this work, the existence of dual morphology of the material. And the nanorods and the nanospheres are present both at the same time. The nanospheres are around 300 to 200 nanometer in size. Now, for the EDX part, you can see that there is the presence of molybdenum and oxygen, which confirms the presence of molybdenum trioxide. And the other peaks are of carbon, because we have used carbon tape to sprinkle the particle for the analysis. For the electrochemical analysis, we see that using cyclophotometry, we have performed for a working electrode that we have deposited on a FTO. You can see that there is only a presence of reduction peak and no presence of oxidation peak, meaning that the material, the working electrode, will gain electrons on to the surface of the molybdenum trioxide working electron, which is a very enhanced behavior because most of the material shows oxidation and reduction peak. But in this case, due to the dual morphology and the anograded nanorods will form enhanced charge transfer behavior, whereas nanospheres will make the system stable, formulate only reduction peak and creating enhanced charge transfer behavior. The diffusion behavior was also confirmed for the material. As you can see on the right figure, that the slope came out to be 0.6 for log of scan rate and log of peak current. If the slope is near 0.5, then it is a diffusion controlled behavior, and if slope is near 1, then it is a capacitive behavior. So as we can see that the present material shows a diffusion behavior. During a potentioimpedance spectroscopy, and we have plotted the Nyquist plot, which shows Warburg diffusion. Now, Warburg diffusion, what Warburg diffusion signifies is that there is an infinite number of electrons present in the working electrode. There will be the surface of the electrode will be covered with infinite number of electrode, which is a very good sign for an solar cell application. Means that this electrode can be used as a thin film layer for solar cell application. So in conclusion, we can see that MO3 nanoparticle was synthesized using low-cost hydrothermal route. The XRD pattern shows single-phase molybdenum trioxide. The crystallite size and strain calculated through various methods shows a crystallite size of 29, 34, 26 nanometer through Debiser, Williamson, and side chain plot. The side chain plot came out to be more accurate than and other both techniques. The UV analysis revealed a band gap of 3 electron volt, whereas FESM confirms the dual morphology of material of nanorod and nanosphere stacked together. The EDS spectra also confirms the presence of molybdenum and oxygen only. The appearance of cathodic plate indicate that there is a high rate of reduction taking place on the surface of MO3. The existence of dual morphology inside a single phase MO3 contribute to amplification of reduction peaks. The nanorod shows increased electron transfer capabilities, increasing higher electron transfer efficiency, while molybdenum oxide spheres contribute to system stability. The slope came out to be 0.5, which shows a better suitability for diffusion controlled solar cell application. And the presence of Warburg diffusion depicts the thin infrared layer of electron has been deposited on the surface of MO3 due to excess of electron present in the thin film. Thank you.
Dr. Poonam Kumari Gautam, Assistant Professor in Bhara University, Shimla Hills. My topic is entitled as Influence of Rotational Effects of Natural Convection Embedded by Jeffrey Nanofluid Sheet in High Porosity. This is the abstract part. This study is based on the two major factors, Brownian motion and thermophoresis. Random movement of microscopic particles suspended in a liquid or gas, such as the continuing erratic behavior of dust particles in still water. The movement is produced by the natural kinetic activity of the molecules of the fluid that strike the foreign particles, also called Brownian movement. Thermophoresis is a phenomena observed in mixtures of mobile particles where the different particle types exhibit different responses to the force of a temperature gradient. Duffer effect. Yes.
Your camera is not on. Is it possible to switch on the camera?
Yes.
Yeah.
1 minute.
Yeah. Right. Okay.
Duffer effect is the every flux due to mass concentration gradient occurring as the coupled effect of irreversible processes. It is the reciprocal to the Surrey effect. The thermophoresis in gas mixture was first observed and reported by John Tyndall in 1870 and further understood by John Strutt in 1882. Thermophoresis in liquid mixtures was first observed and reported by Carl Ludwig in 1856 and further understood by Charles Surrey in 1879. Introduction. Non-Newtonian fluids are used in different industries and find important applications in various fields of science and technology, such as manufacturing of plastic polymer industries, dyeing of papers and textiles, food processing, geophysics, and biological sciences. With the relevance of non-Newtonian nanofluids in modern science and technology, various constitutive relations have been derived in the modeling of non-Newtonian fluids. One such type of constitutive relation is the Jeffrey non-Newtonian nanofluids model. Jeffrey model is linear model that uses time derivative instead of convective derivative. Rotation plays an important role on thermal convection and has various applications in different fields wizard in nuclear reactors and thermal power plants. Understanding thermal instability in nanofluids under the influence of rotation can help in optimizing cooling system and improving heat transfer efficiency. Keeping in view the various applications of viscoelastic nanofluids specified above, the main aim of this paper is to study the effect of the Jeffrey parameter, rotational number, and various other parameters in a porous sheet. Here I have applied the Jeffrey model. These are the applications of Jeffrey model: food processing, filtration, oceanography, limnology, geophysics and engineering, and soil sciences, etc. This is the mathematical model from the where the problem is taken, and these are the governing equations from 1, 2, 3, 4, 5, and these are also the equations with the boundary conditions. But I have applied the stress-free boundaries. These are the non-dimensional parameters which are used here. These are the perturbations used in the equations, and the normal mode analysis and Glergit weighted resolute method is used. After using the method, we get these type of equations, and in the end we get the Rayleigh number, which is shown in equation 24. Natural convection, non-oscillatory convection, this is given in equation 28, and numerical results and discussions. To examine the impact of different parameters, we analyze the nature of the natural convection with respect to the Jeffrey parameter, rotational parameter, Darcy number, Lewis number, and thermodynamic numbers, and Rayleigh nanoparticles numbers, and also the porosity. These are the analysis. From the graphs we can see when we take the different values for the Jeffrey parameter lambda, then the Rayleigh number here increase. And when we put I have considered two distributions, two configurations, top heavy and bottom heavy. So this case for the bottom heavy, and this is the rotational part where the impact is also seen with the Jeffrey parameter, Lewis number, and the Rayleigh nanoparticles number. And this is for the Darcy number for top heavy configuration. Conclusions. The investigation reveals that the Jeffrey parameter has a stabilizing effect on the stationary convection for both bottom heavy and top heavy nanoparticles distributions. The rotation and Darcy-Brinkman number have stabilizing effect on the stationary convection for both bottom heavy and top heavy nanoparticles distributions. This indicates that an increase in the rotation and Darcy-Brinkman number promotes stability and reduce the likelihood of turbulent behavior in the system regardless of the nanoparticle distribution. By manipulating rotation and the Darcy-Brinkman number, practitioners can effectively promote stability and mitigate the risk of turbulence, thereby optimizing the performance of systems where stationary convection plays a critical role. For the bottom heavy nanoparticle distribution, the Lewis number and the modified diffusivity ratio have a stabilizing effect On the other hand, for the top-heavy nanoparticles distribution, these parameters can destabilize the system. The nanoparticles Rayleigh number has a destabilizing effect on the system. The nanoparticles Rayleigh number serves as a critical indicator of the system's predisposition toward instability. As this parameter increases, it signifies a greater dominance of buoyancy forces relative to viscous forces. This heightened buoyancy effect disrupts the equilibrium of the system, leading to the destabilization of convection pattern. The medium porosity can either postpone or enhance the occurrence of convection depending on the distribution of nanoparticles. For the bottom heavy nanoparticle distribution, medium porosity enhances the convection, while for the top heavy nanoparticles distribution, it delays the onset of convection. And this is the limitations. The current exploration of the impact of rotation on thermal instability in a Darcy-Brinkman porous layer filled with the Jaffray nanofluid has several limitations. It often relies on simplifications and assumptions that may not fully capture real-world complexities. There is often a shortage of comprehensive experimental data to validate theoretical models. Future scope. In this study, we investigated the influence of rotation on the thermal instability of a Darcy-Brinkman porous layer filled with the Jaffray nanofluid. Our research serves as a foundational exploration that can be extended to examine the impact of magnetic and electric fields with potential applications across various.
This is Prakash Gadpelle. I'm working as the assistant professor in the Department of Chemistry, Humanities and Basic Sciences, Aditya College, Engineering and Technology. Sir, so regarding this, here to explain what are the synthesis and recent advances, broader significance in chemistry. So most of the the synthetic methodologies, what are the going catalysts are involved in the reaction, and asymmetric synthesis and sustainable synthesis process, what are is going in the reactions, and their and one more thing is there, the artificial intelligence and machine learning, which how the helps in the reaction mechanisms, and what are the applications we are let me know. And challenge and ethical effects and the future synthetic and which are applicable to the chemistry. The next page. The next page. Yeah. Here, what are at least means the in the reactions we are definitely apply the catalyst because of going to the reaction. It is catalyst plays a vital role in the reaction. So we the different type of that most important, and the product, which type of product it will be given, that is at an atom economy, and which type of products it is usable or not. Green synthesis also in okay. Coupling reactions and metathesis reactions and organocatalytic reactions, which are most probably involving in the reactions. Next slide. Sir, here, acceleration chemical reaction remain unchanged at the end of the process. So, in between the reaction, the help of catalyst, we got a product, and the catalyst. That and specific reactors has also dictated the economy and selectivity of the reactors. We are going to use here one example here, acetic hydrogenation reaction. Mainly acetic acid undergo the reaction. Here we are using one of the researcher explained chemistry is the complete reaction of the load in the reaction. The
Dr. Prakash,
metal
Dr. Prakash,
phase. Yeah.
Dr. Prakash,
Okay.
sir,
Yes.
your voice is not audible.
Yeah. No.
There is a lot of echo and
No.
some kind of
Is
noise
it
is there. Maybe some technical issue or network
actually
issue you are facing right now.
no. Actually, I'm audible, ma'am. Is it okay?
You are audible?
Hello?
Actually, there
Yeah.
is
Yeah,
lag
I'm
in the
audible.
voice, Prakash.
My voice is loud, ma'am. Hello?
Yeah, there is a lot of disturbance in your
Hello?
voice. Hello?
Sir,
Now continue, let's see.
present.
Dr. Prakash, you just continue, let's see.
Yeah. Sir, no, sir. Is audible?
Your voice is not coming, Dr. Prakash.
So my side is no problem, sir. I'm
Okay.
completely okay.
Now you continue, yes.
My side. Yeah. The next slide, sir. Next slide. One more example is there. Sir, my idea is audible.
Yes, yes.
Okay. Next. Okay. Next, one more example in the catalyst using reaction, cross coupling reaction. The evolution of coupling reactions, the catalyzed by transition metal. Here, the example is transition metal with alkene reactions, which gives completely, according to the researcher, completely gives only ethylene compounds with the help of palladium catalyst. Okay, which eliminates the small simple molecules by condensation reactions like hydrogen halogens. It is very most efficient reaction in the synthetic chemistry. Uh, transmit very. Sir, next slide, please. The reaction is also undergo the nickel catalyst. Next one, atom economy. The catalyst played a pivotal role in the promoting atom economy. The concept emphasizes the efficient utilization of atoms. Okay, here he explains what are the atoms involving in the reaction, what type of utilization here based on the catalyst, what type of products will give based on the reactions. It explains. So which type of reactions involving in the reactants, that reactants, which type of products will give a completely the reaction completely based on the product, it is useful or not. Okay. Next, one more example, olefin metathesis. Olefin metathesis. Sir, my voice is audible, sir? Sir, next slide, please. Okay. Next, green synthesis. Here, completely green chemistry, the solvent-free reactions is known as the neat reactions, which means there is no byproducts because we are going to prepare some novel material due to the reactants involving in the reactions. The damn sure products we are going to prepare. There is no byproducts in reactions. The reactions is for green reactions. Okay, it is completely, it helps us to modern chemistry. So next slide, please. The next slide. Okay, here the computational chemistry also help us to give a brief in detailed concepts on the chemistry in synthetic chemistry. Here the reactions, how computational chemistry and artificial intelligence help us to different type of reactions. One more example is there, molecular docking. Here molecular docking in between the two molecules, which type of orientations which are going to be attractive on the target molecule and binding site. Okay, lock and key theory will explain, and fragment based reactions, as well as we know already target site and ligand molecules, the orientations, fragments, conformational analysis, fit and induced theories. Those are the things we are going to clarify through the computational chemistry before the go to the other calculations, which is first to which type of reactions undergoing, which type of products will come for the reactions. That will be major pivotal roles placed in the synthetic chemistry, that is computational chemistry. Okay, here the reaction predictions and drug designing, which is most probably this is technical area completely depends upon the drug designing. So the computational chemistry we are completely depends upon the drug designing, which type of reactions we are going to produce. Let's suppose the cis type of reactants which not undergo the reaction, we are going to next level. The reactant is converted into trans, means transformations or rotation in the molecule, so with the help of conjugation and heterogeneity. So the conversion after that, the reaction is going to be in the presence of catalyst, it is gives a usable products. Okay, with the help of we are calculating algorithms and computational chemistry. So next slide, please. Yeah, one more. Next slide. Between the next slide. Yeah, here quantum mechanicals and transitional state models and virtual catalysts in the depth of mechanics undergo the unprecedented accuracy and efficiency. Okay, these are already we discussed here. Different type of molecular dockings, different type of reactions, virtual catalysts, drug designings, and transition state modeling for selectivity. The reaction in between the reactants, which gives intermediate products, that is also used to prepare the green products, which is may help us to know the very pure products. That's why we are completely depends upon the computational chemistry and unpretended accuracy and efficiency. The advantages computational methods have to do lead the accuracy and reliable productions and the strength of designs with the confidence. So next slide. Here, look at the picture, the molecular spectroscopy and complex molecular dynamics and the molecular material science and drug discovery. Okay, here completely these are the chemistry is conclude that in the reaction step drug discovery, in the field of drug discovery, in the field of material science, in the field of complex molecular chemistry, in the field of spectroscopy. Okay, we know already the spectroscopy, how the spectroscopy is help us. If a molecule is contains isomers, okay, that IR spectra completely gives us which molecule is, if it is either alcoholic, it is ketone or it is aldehyde. Based on the IR spectra, we can easily conclude that. And IR spectra also estimate the vibrations based on the different type of molecules. We can conclude and easily. Okay, these are the conclusions in nowadays. We can easily identify the unknown molecular shapes, bonds, and angles, molecular weights also in different. The next slide, please. Asymmetric synthesis. It is also one type of synthesis. Okay, which is it is completely help us in the drug development. Okay, if we know if we are going to prepare a drug, okay, that is 10%, 15% is help us to utilization. But in the drug undergo the asymmetric synthesis, which is help us to the modification in the reactions with the help of catalyst. So the utilization is increased. Okay, that's why we in the drug development the synthesis of asymmetric is a very efficiency used in the next slide, used in the reactions. Next slide, please. Yeah, next slide. Next slide. Yeah, next one, the innovative material applications. Okay, here the allotropes. Example is graphene. Allotrope is a carbon-based material. Is like natural material is there. Diamond. There is the chemical composition is same, but there is a lot of difference. Here graphene is a slidey material, and graphene is a covalent bonded very strong material. That is very different materials. Yes, graphene is a very innovative material. This is used as a this is used as a sensors and catalysts and in the field of electronics used as a membranes. Okay, these are the we are going to prepare if one material, that material is going to be a innovative material, that is very crucial in the preparation of reactions. So next slide.
Dr. Prakash, you have 1 minute only, huh?
Yeah, yeah. Sir, can I start?
Yes, continue.
Uh, in the field of, okay, the graphene is used as a electronic device. Uh, uh, in is used capacitor, it holds the huge amount of current, okay, which has the graphene is used as a electrodes in the cells, okay. It is used as a graphene also used in the medical applications. I can conclude only taken one material, that is innovative material, graphene. So next slide, please. It is also used in the water purifications. Okay, next, bioconjugation, mixing of proteins and mixing of ligand with heavy macromolecules, which gives a uh, good product, green product. Okay, in the field of drug delivery applications, the imaging applications, and applications of diagnostics, very essential uses. Next slide. Okay, trajectory materials and diagnostic therapeutic. This is the very targeted products we are going to prepare with the help of bioconjugation and therapeutic antibodies also involving in the reactions, bioconjugation instrumentational in the development of therapeutics and treating the various diseases, including the cancer and uh, autoimmune disorders. Okay, so next slide. Biotechnology also will help us very most essential uses in the green chemistry and as well as the synthetic chemistry. The green chemistry principles explained by Antust and Warner in 1980. 12 principles is there. Okay, which is mainly used in the reactions, which type of product is given, which type of reactants involving the reaction, what are the intermediates, and what are the reaction rates, what are the dynamic of the reactions. Okay, these are the completely explained through this one slide. So next slide. The atomic. Okay, these are the five most probably key points to explain the green principles, atom economy, and solvent selections, and different type of reactants involving in the reactions, and different type of designs of the products which are going to be used. And next, energy efficiency and safer chemicals are going to be used to prepare the new products, and safer chemicals are going to be used to involving in the reactions, and the life cycle of the assembling life means which type of product we are going to be prepared, that product is the how much of period it will be usage in the field. So next slide. Thank you.
Hydrogel 100 microgram per ml, the cells were able to survive and they so not so cytotoxic. The next please. And this is the wound healing assay that we conducted. Here you can see in the panel A control cells, we made the scratch in the center of the slide and the geographic cell line. And after 36 hours in the down, you can see the cell were able to proliferate, but it was not all of the area was completely healed. While in case of the right side, you can see when we applied in the middle of the panel, we can see when we applied our hydrogel, and at the 0 hours we had made a big scratch, and while at the end of 36 hours you can see in the middle the cells were able to regrow, so it shows its own healing properties. So next. Thank you very much, that's all. If you have any question you can ask me.
Thank you, Dr. Vinay.
Thank you, sir.
Any question from the audience side? Any question? Okay then. Thanks. Thank you very much, Dr. Vinay, for the presentation.
Okay, sir. Thank you very much.
Yeah. Now, Dr. Prakash.
Yes, sir. Please, please share my PPT. Already
Yes.
sent to your console. Yeah.
I think so. Slides
Okay,
are
first,
visible.
yes, sir. Yes.
Yeah.
Can I start
Continue. Yes,
Okay.
yes.
Thank you, sir. This is
So good afternoon, everyone. I am Pranati Purohit from Gangadhar Meher University, Sambalpur, Odisha. So I am going to give a talk on this moving from lead to lead-free piezo ceramics. So what are piezoceramic material, or what is piezoelectricity? Piezoelectricity, basically it is the ability of a non-centrosymmetric material with the general formula of AbO3 type, where A is a divalent caption and uh, this B occupies the center of the cube, and in this material, when we apply some pressure, they generate the electricity that is called as the direct piezoelectric effect. And this we also get the reverse piezoelectricity. By applying this high voltage, this materials also get deformed. That is called as the reverse piezoelectric effect. And these materials are basically of this peroxide structures. So let's move to the introduction of this why to move from lead to lead free. So basically, piezoceramic devices, they play important role in various industrial and research applications as sensors, transducers, actuators, etc. The most commonly used piezoceramic today are lead-containing material, and due to their high piezoelectric property and the possibility of their application, adapted shaping, ease of fabrication, these piezoelectric ceramics based on these lead-containing peroxides are chosen as the active material for most of the piezoelectric applications. However, it is well known that lead is toxic in nature, and as it deposits in various parts of the body, it leads to different types of diseases. So in this context, a review article focusing on the comparative study of lead content and lead-free systems would be helpful in finding a new lead-free materials for the research. So what are the lead content piezoceramic materials? The first one is the PZT, which is also known as lead zirconate titanate. The most promising material, piezoelectric material, it was discovered in 1952, and this material is very popular and exhaustively studied piezo systems, which allows the synthesis of large number of materials with wide range of properties due to the formation of solid solutions over the range of this by changing the zinc to titanium ratio. And this system accommodates wide range of dopants for modifications of the crystal structure. In order to enhance the piezoelectric properties, some binary piezoceramic materials are there. These are the combinations of different materials. For example, this PMN PT material, which is lead magnesium neomate and lead titanate. In these piezoceramics, these are advantages over other piezoceramic materials because this material is very cost effective, ease fabrications, and the morphotropic phase boundary of this material occurs at the when X is 0.29. So this PMN and XPT. So this is PMN is 1 minus X and PT is X. So in this way, it is found that this material shows maximum piezoelectric property when the X is around 0.29, and this is the most cost-effective material. And this material can be easily synthesized by the simple solid-state synthesis method. The next binary material I'm going to discuss is about this PNNPT. PNN is lead nickel niobate, and this PT is lead titanate. So by combining this lead nickel niobate and lead titanate, this PMNPT, it is also a binary piezoceramic material, and this was formed, and it is found that this material, by taking the different combinations, it is found that this material also shows good piezoelectric property, that is also known as the D33 property. When we move to the other lead-based material, those are called as ternary relaxer material. These ternary relaxer materials, for example, here I am discussing three types of material, that is PIN, PZN, PT, means lead indium niobate, lead zinc niobate, and lead titanate. When we combine these three materials to form this ternary relaxer material, then it was found that the combination, that 0.40 PIN and 0.33 PZN and 0.27 PT composition, it shows maximum dielectric loss, and this also shows a high D33 value, which is called as also known as the piezoelectric coefficient, that is 589 picocoulomb per Newton. So when we move from this PZT to binary material, then to ternary material, the piezoelectric property of these materials are going on increasing. So the next ternary material is PZN, PMN, PT. So this PZN stands for lead zinc niobate, PMN is lead magnesium niobate, and third one is PT is lead titanate. By synthesizing this material with the Coulombite precursor method, it was found that the composition, this 0.64 PNN and 0.36 PT with PZN of 0.91 and PT of 0.9 ceramic with various values of X, the composition with X is equal to 0.15 lies within the region of this morphotropic phase boundary, and this gives the highest D33 value, which is also known as piezoelectric coefficient of 600 picocoulomb per Newton. Then the next piezo ternary material was synthesized by this Yamashita and group, and they studies various physical piezoelectric properties of ternary ceramics. And this material, that lead PSN, PMN, PT, that is lead scandium niobate, lead magnesium niobate, and lead titanate. So this mixture near the morphotropic phase boundary, they found out the maximum D33 value of 680 picocoulomb per Newton. This is the piezoelectric. This is also known, this D value is also known as the piezoelectric coefficient. The dielectric value is around 3,800. The dielectric constant, the Kp value, and that Curie temperature is around 200 degree. So if we are getting the high piezoelectric value or piezoelectric coefficients with the this lead-based ceramics, then why to move to the lead-free? Because this lead-based piezoceramic materials, the different countries, they ban on the use of lead. And these lead-based piezoceramic materials and environmental concerns. So different times, the different researchers groups, they showed that the lead-based that PZT, which is lead zirconate titanate, which is mostly used piezoceramic material. It contains lead oxide more than 60%, and this and the other researchers, they also discuss that that this lead, the lead is a hazardous material, and we should restrict the use of lead. In 2004 and 2007, Saito et al. And Zhang et al. They published the articles to stop the use of lead. And again, this different countries, they ban the use of lead on different materials. We have also heard that this lead-free paints are being used now, and many government regulations of different countries, such as United States and EU, they also imposed ban on the use of the toxic use of lead. So when we synthesize the materials, and after the use of these materials, when we decompose, when we let the material free, they mix with our water and the soil. And when we consume these materials, they cause very hazardous diseases. So it is now time to move from these lead-based materials to the lead-free materials. So that we can live in a healthy environment. So I have discussed few lead-based materials and their piezoelectric coefficients. That is the D33 value. Now I am discussing some lead-free piezoceramic material. And in this paper, I am focusing on the ceramic part. I am not going into the single crystal, piezoelectric single crystals. Piezoelectric single crystals, they show high piezoelectric coefficients in comparison to the ceramics. But the ceramics can be easily, so the synthesis is easy. So that is why I am going for the piezoceramic part. Now I am discussing few lead-free piezoceramics. Now, piezoelectric ceramic materials without having lead oxide, that is PbO, in its composition are called lead-free piezoceramics. So earlier, the materials which I have discussed, in all the materials, that is lead oxide is there. So these lead-free piezo materials were developed during 1950, at the same time when PZT was discovered. So these lead-free and lead-based piezoceramic materials are discovered at the same time, but due to the very less piezoelectric properties of these lead-free systems, so researchers focused on these PZT-based materials, that is lead content material. So, but as the time passed and the vast use of this lead-based piezoceramics threatened human life and caused environmental pollution due to the toxicity of the lead oxide present in this material. Therefore, the research on the lead-free materials, which are nearly stopped in the 1990s, now gain momentum in the recent years, and the research is going on to synthesize or to make these lead-free piezoceramic materials, which will show high piezoelectric coefficients. Some of the lead-free peroxide, this ceramic materials are barium titanate, that is BT, barium titanate, BiNaTiO3, or it is also known as BNT, BiKTiO3, it is known as BKT, and this KNaNbO3, which is also known as KNN. Now I am going step by step to discuss these lead-free materials. So the properties of these lead-free materials. So this lead-free piezoceramics, I will start with this barium titanate, which is commonly known as BT. It is BaTiO3. This barium titanate is the first polycrystalline lead-free piezoceramic materials. It is first discovered during the World War II, At the same time, when this PZT was discovered, the piezoelectric coefficients of this BaTiO3, which was synthesized by the solid state processing or synthesis method, it was found out to be 190 picocoulomb per Newton. In other work, this piezoelectric coefficient of 460 picocoulomb Newton is reported in when it is synthesized in high quality
ma'am.
hydrothermal.
Sorry,
Yes.
sorry to interrupt you, ma'am.
Yeah.
Last 2 minutes you are having this. Actually, we are
I'm
having only 15 minutes, 13 minutes, and plus 2 minutes for the question and answer. So
okay.
kindly
Okay.
summarize.
So how much time I'm left? I'm left with.
Just 2 minutes, ma'am.
Okay. I'm moving quickly. Okay. So the other materials are barium sodium titanate, and this material shows the piezoelectric coefficient of 98. And this bismuth potassium titanate, that is BKT, it has got the piezoelectric coefficient of 69. So when we are discussing about this lead-free system, they are showing very less piezoelectric coefficients. And when we, for example, this KNN system, they show this 80 to 160 picocoulomb per Newton. And the binary system of these materials, that is BNT, BKT, this shows some improved piezoelectric coefficient, that is 140 to 190 picocoulomb per Newton. And this the other material, that is this is the BZT BCT system. It is a binary lead-free piezoceramic material. It shows a high piezoelectric coefficient, that is 620 picocoulomb per Newton, when this material is at the tri-critical point, that is TCP. Here this TCP is the diagram of this TCP is explained here. So if we synthesize some lead-free material and make them to this tri-critical point, then we can get the high piezoelectric coefficients. And this is the table showing the piezoelectric coefficients of the some of the lead-based materials, and they are showing very high piezoelectric coefficients, around 600. And this is the piezoelectric coefficients of BNT BKT system. And when we see the D33 of value of this, we are getting maximum up to 192. And when we move to the other this lead-free system, so we are also getting the maximum is around this 300 to 400 picocoulomb per Newton. So it is found that these lead-free systems, they show the less piezoelectric coefficients. But if we synthesize these lead-free materials with the different combinations, we can increase the piezoelectric coefficients. So this is the comparison of this lead content and lead-free ceramics. So lead content ceramics are well verified. They are now applied into different systems. But the lead-free piezo materials are in the development stage. They are still going on, and researchers are working on to increase the piezoelectric coefficient and also the Curie temperature, so that this can have the device applications. And in my conclusion, I can say that the properties of various lead content and lead-free piezoceramic materials we have discussed in this paper. Now, the lead-free systems cannot compete with the lead-based system, that is PZT, which is commercially available. But if we synthesize the lead-free materials with suitable composition, and if we increase its electromechanical properties, then this lead-free ceramics with high piezoelectric properties can be developed as an alternative for these lead-based systems, and without polluting our environment, we can fabricate the device so that it will be helpful for the for us.
And these are few references which I have taken for this study of this paper. And thank you.
Thanks to the organizers for giving me the opportunity for the second time as the invited speaker in this conference. So today my talk is the guiding selection of correct ingredients to realize host-sensitized dopant emission. And in most of the part, this dopant will be F-block dopants, that is the lanthanides. And the later part of the talk, I will be moving on to the D-block dopants. So the uniqueness of using the trivalent lanthanide luminescence are their sharp bands, as we can see in this panel, compared to the very broad bands of typical organic fluorophores. So which means that they have a minimum intra and inter-lanthanide overlap, and consequently they have a very longer lifetime in the range of microsecond to millisecond, which can be easily distinguished from the nanosecond-lived autofluorescence from typically biological media. And one can see that using this kind of, let's say, terbium incorporated or doped zinc sulfide nanoparticle, one can realize both the emission in the UV blue and green region from a single luminescent system having two luminescent centers. Now, however, to use lanthanide luminescence for practical purposes, the intrinsic challenges are their inefficient direct excitation and the environmental induced emission quenching processes. To overcome these challenges, one way to realize is to dope these lanthanide ions, cations, in an appropriate semiconductor nanoparticle matrix, where this nanoparticle can act as an optical antenna, that is a sensitizer, as well as a protector matrix, which we can see from these lifetime measurements that in a case of bulk solvent, the lifetime is way faster. This is around 4.8 microsecond only, whereas in the nanoparticle, their emission is significantly lengthened. And now one can think about the applications of these doped nanomaterials in any applications, like in any luminescence-based applications like biological imaging, bioanalytical applications, sensing, and so on and so forth. Now, with regard to the synthetic strategies to dope the lanthanides or the dopants, we have used either a synthetic incorporation strategy, where the lanthanide is incorporated in the synthesis during the synthesis of the nanoparticle, and or the post.
Sorry to interrupt you, Dr. Prasoon.
Yes, ma'am.
Your PPT is not moving. It got stuck on the first PPT. You have to just click on the PPT you want to show.
I did, and I checked. Okay, let me do it again.
Yes. Now the second PPT is shown. Yes, sir.
So now it's second, right?
I think you have to just click on the PPT.
Okay, then the full screen will not be.
No issue, sir. We can see it properly. No issue with that. But just
okay,
you have
fine,
to click.
Fine. Then it is fine. Okay, but then ignore. So now you can see only the second slide, right?
In which you have just click it on. We can only see the second slide.
Right, but then.
Yeah, now it's been written here, lanthanide cation, Ln3 plus luminescence.
Yes, I understand. Okay.
It's there.
So, now you can see the third slide.
Yes, we can see it.
Okay,
it is
fine.
Nanoparticles,
Fine.
act as antenna.
So,
yeah.
That is the slide I was discussing just now.
Okay.
That
okay.
In case of, if we dope the lanthanides in an appropriate semiconductor nanoparticle matrix, this can act as an optical antenna. So they will be absorbing the light efficiently and then transfer energy to the lanthanide center, as well as they can lengthen the lanthanide emission lifetime significantly, which we can see here. Okay, and these luminophores can be used as in any photoluminescence-based applications like biological imaging, bioanalytical applications, sensing, and so on and so forth. Okay, now So just to make sure now, can you see the fourth slide with the synthetic strategies?
Yes,
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 sir.
it's there.
Thank you very much. Thank you very much for the confirmation. Okay, thank you. So with regard to the doping strategies, we have either used the synthetic incorporation, where the lanthanide was introduced during the synthesis of the nanoparticle, or a post-synthetic doping strategy, where first the nanoparticle is formed, and then the lanthanide is introduced to form the CaLN. So to distinguish between these two, the nomenclature in our methodology goes like within the parenthesis Ln means it's the synthetic doping. After the slash Ln means it is the post-synthetic doping. So an important question lies that what is the correct combination of the host nanoparticle and guest Ln3 plus combination so that this optical antenna effect can be realized properly. So just these are the topics that I will be discussing today. So first subtopic will be on the 2,6 sulfides and selenized, and then we proposed a mechanism. So early work by Stefan Pitud and co-workers, they have showed that if terbium is doped in cadmium selenide nanoparticles, one can have the optical antenna effect, which can be judged from the time-gated excitation spectrum. And this time-gated spectrum means we have a delay time, and then in that delay time, all the nanoparticle emission is died down, and then the longer-lived emission is collected with a gate time, longer window gate time. So later on, but this system, cadmium selenide terbium incorporated in cadmium selenide, is having a lower kind of efficiency, so that needs to be improved. And the other important issue was basically cadmium being a little bit on the toxic counterpart of the periodic table. Okay. Now, later on, we have demonstrated that terbium and europium sensitization can be very efficiently achieved by zinc sulfide as the host material. And here we can see that this, with respect to the other sulfides and selenide, zinc sulfide is more efficient, which is sensitized by the nanoparticle, and the lifetime is also lengthened, which we can see in this middle panel. And later on, we have seen that cadmium selenide Ln and zinc sulfide Ln, this europium and terbium, and in addition, ytterbium can also be sensitized in case of zinc sulfide. So with this, we tried to rationalize these experimental observations by a charge trapping model, where if we look at this zinc sulfide panel, terbium panel, this x is equal to 8 is terbium, we can see that the ground state, ground energy level, and the luminescent energy level, they lie appropriately above and below the valence band and conduction band of the host material. That is why the zinc sulfide is a very efficient host to sensitized terbium emission. Whereas if we look at, say, cadmium selenide, here we can see this is an extreme case that the luminescent energy level lies above the conduction band, hence autoionization is very prone, lessening the efficiency of the emission. Later on, we have also, based on this confirmation of this energy level diagram, we have energy level proposal that we have also confirmed that a lesser size, smaller size of nanoparticle is better efficient, is more efficient in sensitizing terbium and zinc sulfide, and their core and surface components evolve, their emissions evolve differently. And then, based on a systematic analysis to analyze or to evaluate the role of spectral overlap between the donor emission and acceptor absorption, we have systematically compared the overlap integrals under Foster and Dexter mechanisms. And in all cases, we have realized that the theoretical calculation prediction based on only the spectral overlap does not match with the experimental observations. So based on that, we propose that this charge trapping and optimum energy offset of this hole trapping and electron trapping, they are very needful to realize an optimum host sensitized dopant emission in these nanoparticles where the spectral overlap is not at all significant. With this, I'll just briefly mention about the nature of the emission lifetimes in these nanoparticles, where in all the cases, irrespective of the operation of the host sensitization or not, the inorganic nanoparticles lanthanide emissions are bi-exponential in nature. So they deviate from a single exponential behavior. And we interpreted this in a sense that the more surface localized components will be quenched, the emissions of them will be quenched, so it will produce a shorter lifetime, and the longer lifetimes will be related to the interior sites or the core sites. And one can see that these are the longer lifetimes. These are significantly enhanced in lifetime compared to the shorter lifetime, and which overlap significantly with the lifetimes in different molecular complexes that we have compiled from the literature. And we later on correlated these trends of emission lifetimes with respect to the vibrational frequency of the immediate local environment. So with this note, then we wanted to verify with a couple of systems that how this charge trapping thing actually correlate with the outcomes, experimental outcomes in different systems. So for that, we performed an experiment where we have compared the band gap matched SN-LNO2 and ZN-LNS. And we have observed that, so we have taken SN-SMO2, SN-TBO2, ZN-TBS, and ZN-SMS. Now, as the band gaps are similar, then, or nearly same, one should expect, if it is a spectral overlap mediated model is operating, one should expect similar sensitization efficiency. Whereas experimentally, we have seen that the sensitization is only present in SN-SMO2 and ZN-TBS, and the other two systems, SN-TBO2 and ZN-SMS, did not show any sensitized lanthanide emission. And that correlates perfectly with the corresponding energy level diagrams and a charge trapping model. Now, in a series of experiments with all the throughout the lanthanide series except the optically silent ones and the radioactive promethium, we have undertaken 11 lanthanides and doped them in TiO2 based nanoparticles. And we have observed that the most efficient systems are the neodymium and samarium doped systems, where again charge trapping is of significant importance. Whereas the other systems, for example, terbium, here the charge trapping would be inefficient in TiO2 and it showed no emission. So for example, here terbium is in the absent column here. Okay. And ND and SM are the most significant sensitized emission were realized. And later on, we took another oxide, which is SNO2, and SNO2 is having a larger band gap compared to TiO2. Now, with respect to the charge trapping model, one would expect that SNO2 will be more efficient compared to TiO2 in sensitizing, say, samarium emission or neodymium emission. Now, experimentally, however, the opposite has been observed, that the TiO2 is more efficient compared to the corresponding SNO2 based nanoparticle. And here we have, based on the asymmetry ratio calculations, etc., we have concluded that in addition to the charge trapping operation of the charge trapping processes, if one can break the dopant local site symmetry, then the Ln3 plus emission enhances significantly. Here is a summary of the entire thing with different sulfide selenides and oxides, etc., where one can see different kind of scenarios. And this is the optimum case where the host sensitization is most significant. And these gaps are very important, because if this gap is very large, then the other non-radiative processes' contribution would increase. And if these gaps are low, then the back hole transfer from here or from the luminescent state and in luminescent energy levels, the back electron transfer would be of significant importance. So these are summarized in these other possibilities. And an interesting case arises when there are multiple Ln3 plus Ln energy levels, either the involvement of Ln2 plus energy level, and if there are multiple luminescent energy levels, then it depends that where exactly the luminescent energy levels are. If it is above the conduction band, the nature is different. If it is below the conduction band, the outcome from that luminescent energy level is found to be different. Now, coming up to the last part of the talk, that we want to revisit with this understanding with this 4F elements, dopants, that lanthanides as dopants. We wanted to revisit the case with the 3D block elements. And in that, what we tried is we have taken this paper by Hart and co-workers back in 2015. She has done some theoretical calculations based on DFT formulations and identified the energy levels of 3D block elements in zinc sulfide. And we wanted to correlate our charge trapping model with respect to the computational feedback that we have in our hand. And one can see, and experimentally, just by the way to convey this message, then experimentally, in case of zinc sulfide doping, the most efficient dopants are found to be manganese emission and copper emission. The second is copper emission. And one can see that this manganese and copper, they are kind of optimally placed. Their ground states are kind of optimally placed with respect to the band gap of the zinc sulfide. Whereas in the other cases, they're either very close, so kind of back transfer, backfold transfer and all can play a significant role. So to summarize, we can conclude that we have identified based on a charge trapping model that which dopant would be more appropriate to incorporate or to dope in an appropriate semiconductor nanoparticle. And most importantly, so we can approach this not by a trial and error approach. Rather than that, we can approach this to select this material with a kind of precise predictive approach. Okay. Lastly, I'd like to thank all the students and my collaborator, Professor Waldeck in University of Pittsburgh, and all of my students who have already, some of them have graduated and some of them are working, and some of other students whose work is not included here. And last but not the least, the funding came from the University of Calcutta, CRNN, the Center for Research in Nanoscience and Nanotechnology. And the extramural research funding has been generously provided by the ACRB, DST, and UGC. And again, I thank you, thank you all, and to the organizers for giving me this opportunity to present our work in the conference.